We charge them every day. Phone, laptop, wireless earbuds, power bank, electric toothbrush, car key fob. We curse them, replace them, buy new ones. But very few people actually understand what happens inside when a battery suddenly gives up. Most explanations stop at chemical reaction between anode and cathode. That's true, but it explains almost nothing about why your phone drops from 40% to 0% in an hour, why it swells after 2 years, or why an old NINA still holds charge after 15 years while a new lithium-ion dies in 6 months. Let's go deeper. First, there are 2 main families in daily use: rechargeable and primary single-use. Primary batteries, alkaline, zinc carbon, are simple. Zinc anode, manganese dioxide cathode, potassium hydroxide electrolyte. When you use them, zinc oxidizes, electrons flow through the circuit. Once the zinc is consumed or the electrolyte dries out, battery dead. They are cheap and stable, but irreversible. Rechargeable batteries are where the real engineering battle happens. Nickel-cadmium, NICD, old school, memory effect, toxic cadmium, but very robust. Still used in some power tools because they tolerate full discharge and abuse. Nickel metal hydride, NIMH, better capacity, no memory effect if you don't overcharge, environmentally friendlier. That's why good AA/AAA rechargeables are still NIMH. Lithium-ion, Li-ion, king of modern devices. High energy density, low self-discharge, no memory effect, but also the most fragile chemically. Here's what really happens inside a lithium-ion cell. You have graphite anode, negative, lithium metal oxide cathode, positive, usually LiCOO2, NMC, LFP, etc. Porous separator, liquid electrolyte, lithium salt in organic solvent. When charging, lithium ions move from cathode to anode, intercalating into graphite layers. Electrons go through external circuit. Discharging, reverse process. The problems start with side reactions. 1. SEI layer, solid electrolyte interface, forms on anode during first cycles. It's good, protects graphite from further reaction, but it grows slowly over time, consuming lithium and increasing resistance. 2. Lithium plating. If you charge too fast or at low temperature, metallic lithium plates on anode instead of intercalating. It forms dendrites, leads to short circuit risk, leads to fire. 3. Cathode degradation. Crystal structure collapses over cycles, especially in high nickel chemistries, NMC 811. Oxygen release leads to electrolyte oxidation, leads to more gas, leads to swelling. 4. Electrolyte decomposition. At high voltage, greater than 4.2 volts, or high temperature, solvent breaks down to gas generation, CO2, CO, hydrocarbons. To pouch cells swell, cylindrical cells vent. That's why your phone battery shows 1% but shuts off. The voltage sags under load, because internal resistance rose dramatically. The fuel gauge, BMS, tries to estimate, but chemistry doesn't care about percentages. It cares about voltage and current capability. Why do batteries age so differently? Calendar aging, just sitting. SEI growth plus electrolyte drying. Even unused battery loses 3 to 5% capacity per year at room temperature. Cycle aging. Each charge/discharge cracks particles, grows SEI, dissolves transition metals from cathode. High state of charge storage, keeping at 100%, accelerates cathode degradation and electrolyte oxidation. Heat. Every 10 degrees Celsius above 25 degrees Celsius roughly doubles aging rate. That's why phone batteries lose 15 to 25% capacity after 500 cycles, approximately 2 years of daily charging, while a well-kept NIMHAA can survive 1,000 plus cycles. Practical tips, real engineering, not myths. Keep lithium-ion between 20 to 80% most of the time. Reduces stress on both electrodes. Avoid full discharge to 0% often. It stresses anode. Don't leave at 100% for weeks, better 50 to 60% for long storage. Heat kills batteries faster than anything. Avoid charging in hot car. Fast charging shortens life. 0.5C to 1C is gentle. 2C plus accelerates degradation. So batteries aren't dying randomly. Every swelling, every sudden shutdown, every lost 20% capacity after a year has a precise chemical and electrochemical reason. The next time your device dies faster than expected, remember, it's not bad battery. It's chemistry doing exactly what physics and material science predict under the conditions you gave it. What do you think? Which device kills its battery fastest for you? Laptop? Phone? Wireless earbuds? Drop your observations in the comments. I read every single one. In the next video, we'll look at something completely different, how corvettes and frigates are built today, and why one small detail decides survivability in combat.